In section 3.3, we'll be talking about integration by parts. That's the second rule of integration after substitution. Our goal in this section is to translate the product rule for derivatives to the integration by part rule for integrals. So as we mentioned in the previous section in 3.2, every rule for derivatives gives a rule for integrals. Some are useful, some are less useful, so we've already seen that the chain rule gives us substitution. And now we'll see that the product rule gives us integration by parts. And again, this one's useless. All right, so let's start like we did for substitution. Let's start with the statement of integration by parts. Then I'll show you how to apply it when you're given some information. So let f and g be differentiable function. Then the integral of f times the derivative of g is equal to f of x, g of x, minus, and now I'm going to take the derivative of f and plain old g. All right, so when you apply integration by parts, really what you're doing is you're replacing one integral with another. Right, so instead of having to integrate this function, you have to integrate this one. And so you're going to have to pick f and g carefully to make sure that the new integral that you have to integrate is easier than the one you started with. Otherwise, you're wasting your time. All right, so in the first few examples, I'm going to tell you which f to use and which g to use. Let's try one. Example 3.3.1. Let's apply integration by parts to the integral of x cos x with f of x equals x. So let's write out what we have. So we're told that this part is f of x. All right, so if I have f of x, the rest must be g of prime of x. So this section right here is g prime of x. All right, to write out the right-hand side of this equation, well, I have f, but I need g, and I need f prime. All right, so we said f of x was x, and so if I want f prime, I'm going to differentiate. All right, so here I'm taking the derivative. Now I know what g prime is, and all I have to do is I have to come up with one g that would work. All right, so here you need an antiderivative. Often, just because we've played with integrals more, you're going to think of it as an integral, but because we only need one of the antiderivatives, you will not need the plus c. All right, so in fact, you could use this formula here with any antiderivative of any choice you want, no, of g, sorry, any antiderivative of g, any choice you want, it will give you the same answer in the end. All right, so here I have cos. I'm going to use our favorite antiderivative for cos. I'm going to use sine. But you could use sine of x plus 5 if you wanted to. That'd be fine as well. All right, so this is the integral of f g prime. So I'm going to write that it's equal to f of x g of x minus f prime of x g of x dx. So f of x g of x, so it's always going to be this diagonal. So that's x sine of x. And then the integral that you'll have is f prime times g. And so it's going to be this integral. So minus the integral of 1 sine of x dx. All right, so instead of integrating x cosine of x, I now integrate sine of x. That's one of the basic integrals, so it's much easier than the one I started with. Integral of sine, I mean, we just did it. It's minus cosine. And so my answer is x sine of x plus cos of x plus c. Let's check. I like to check whenever we apply a new rule. I want you to see that really the reason why it works is partly because of the product rule. All right, so I need to check that the derivative of this will give me the original function. And so the first thing I'll do is I'll apply the product rule here. So I'm going to get 1 sine of x plus x cos of x. All right, so I apply the product rule here. One of the term will be the one that you wanted. The other one we need to cancel, and that's why at this point we made sure that we had an antiderivative for sine so that it will, when I take the derivative, cancel with this one. All right, so I get minus sine of x, and so all in all, I get x cos x. Perfect. All right, so really the point is this function will have two parts to its derivative. One will be this one, and one will be that one. That's how we'll prove the result in the last section of this part. All right. This is fine. It's a bit cumbersome to have f and g, and so what we'll do is we'll use variables like we did in substitution. So to simplify the notation, we'll use u equals f of x and v equals g of x. Now from substitution, we learned the notation du, and it stood for f prime of x dx, and dv would be g prime of x dx. So using that, we can rewrite integration by parts. Here's the original statement. Integral of f g prime equals f g times the integral of f prime g of x. So f we said was u. G prime dx, that would be dv. And so u dv will be the first term. Now f and g is just u and v from here, and so that's not too bad. And then here I'll have g of x, that's v, and then everything else, this part, that's du. All right, so whether you write it like this or you write it like that, it's the same result and it's going to be useful in exactly the same way. All right, so this is often the one that people remember. So let me put a heart. Just to make sure that you remember it. All right, integral of u dv is uv minus v du. All right, so in example 3.3.2, we'll apply integration by parts with this new notation, and I'm going to give you u. And then in the next section, we'll learn how to pick u amongst the function involved in your integral. All right, so in this case, we're told that this should be u, so everything else needs to be dv, because the integral I'm looking for is u dv. All right, so what I'll do every time, I'll write u and dv, the two parts that make up my integral, on the left of a little table. Notice that because I'm using dv, I must include dx now. Then we're going to do the same thing we did over here. I'm going to take the derivative of the top and the antiderivative. I'm going to write it as an integral just to make things a bit less confusing. So here, I'm going to take a derivative, and here I'm going to take an antiderivative. Well, let's write it as an integral, and in parentheses, no plus c. All right, so the derivative of 2x plus 3, that's going to be 2, and I'm going to put dx. That's going to give me du. So du is 2dx, and then when I integrate dv, I'm going to get v, and v is going to be, I don't know if you remember this, but we actually learned how to integrate this. It's e3 to the x over 3. Okay, so this one was takeaway number 1. All right, so now that I have all my pieces, I can write out the right-hand side of this equation. So my original integral, I'm going to often do this, call an integral I so that I don't have to repeat it completely. It's u times v minus v du. So u times v is going to be this diagonal. So 2x plus 3 e to the 3x over 3 minus the integral of v du. Integral of v du is e 3x over 3 2dx. All right, so this part is already integrated. I don't have to integrate anymore. And this part, I'm going to just integrate and then I'll be done. So I have 2x plus 3 e to the 3x over 3 minus 2/3. I'm just going to pull out the constant and then integral of e to the 3x. I have it here. It's e to the 3x over 3. And so I'm getting 2x plus 3 e to the 3x over 3 minus 2 e to the 3x over 9 plus 6. All right, let's do another one. Let's say I have to integrate log of x, and I'm told to take u equals log of x. I'm going to use integration by parts, so let me write u. Oh, actually, let me write it a bit below. And then dv is everything else. So I took u to be ln of x, so dv is going to be dx. That's a bit strange. One thing I could do is I could write it as 1 dx. Maybe that's going to be easier to integrate. And so I'm going to take the derivative. I get the du is 1 over x dx. And then I'm going to take an integral. So I need an antiderivative, really. Antiderivative of 1 is a function whose derivative is 1. The easiest one is x. All right, so again, you take this product minus the integral of this product. All right, so uv is ln of x times x, and minus v du, that's minus x, 1 over x dx. So I get x ln of x minus the integral, the x actually cancel here, and I get 1 dx. And again, the integral of 1 is x. As I've mentioned before, when we did the basic rules, you don't need to add a plus c until the last integral is done. So as long as I have an integral, I don't need a plus c. Same thing here, right? I have an integral left, so I don't need a plus c. I can wait until the last integral is gone. So here, that was my last integral. Once it's gone, I put a plus c and I keep it till the end. All right, so in integration by parts, you'll be integrating things like that often. And so that's part of the reason I put these results in takeaway 1. Let me write it here just so you have it nearer to the places where you'll use them. So what we said in takeaway 1 is using substitution, we got that the integral of cosine was 1 over a sine of ax. Sine was 1 over a minus cos of ax. Remember that a was there to cancel with the a that comes out of the chain rule? And same thing here. So whenever the inside of your function is not x but ax, all you have to do is add an extra 1 over a in front and everything works out well. In the next video, we'll be talking about how do you pick u. At this point, we know how to apply integration by parts if we're given u, but of course on an exam, I will never give you u. You'll have to figure it out for yourself.